Welcome to 10.2 Part 1, Combinations. In this lesson, you will learn to find the number of combinations of elements from a given situation. You will also be able to determine whether to add, subtract, or multiply combinations by the end of this lesson. The main difference between combinations and permutations is order. In both combinations and permutations, the idea is that you are taking elements out of a set of elements or list of elements. In a permutation, order matters. For instance, a permutation might solve a problem like, if you have a race with 20 people, how many different ways can you have 3 people finish in first, second, and third place? There you're taking 3 people from the 20 people, and you're putting them in first, second, or third place. In other words, order matters. A combination, however, might be a situation like this. 20 people are running to be on a committee of 3 people. So in other words, in this case, you are taking 3 people to be on the committee. However, their position on the committee is not different from one another, so it doesn't matter what order you choose the 3 people from. Let's look at an example. It might help clear this up. In our last video, we had an English assignment. In this English assignment, we were asked to choose 2 books from a list of 5 books. One of those books we would write a paper on, and the other book we would do a presentation on. This was an example of a permutation because when we chose those 2 books from the list, we did different things with them. In this example, I've got a slightly modified version of this assignment. Here I'm asking you to choose 3 books from a list of 5 books and write papers on all of them. This is a combination situation because you are writing papers on all 3 of the books. I'm going to call my books different things. I'll call them Book 1, Book 2, Book 3, Book 4, and Book 5. And then I'm taking 3 of them, so I'm going to put 3 slots out there for me to put the books into. And here's just a possible selection of books. I could choose Book 3, Book 2, and Book 5. Why not? So, if order mattered, and putting 3 in the first slot instead of 3 in the second slot made a difference in my selection, we could figure out how many different ways there was to do this by doing what we did last time, where we said, okay, I've got 5 books. I will go over to the number of permutations on 5 books, NBR, and then I'll choose 3 books. There are 60 different ways to order 3 books out of 5. So that's an interesting piece of information to know there. However, let's look back at our example. I'm choosing 3 books and I'm writing papers on all 3 of them. So if I chose Book 2 first, and then I chose Book 5, and then I chose Book 3, would it really make a difference? Not really, because I'm doing the same thing to all these books. I'm going to write papers on them. So it doesn't matter which slot I put the books into. It just matters what the numbers are in those slots. Well, what are some other possibilities for the way I could arrange this? You can look and see. These are all different. And I know for a fact that I'm done. How do I know that I'm done? Well, I chose 3 of those books, and then I'm asking how many different orders can I put them in? But we know what that is, right? I choose 1 for the first one, say I chose 3, and then I could either choose 2 or 5 next. I'll choose 2 in this case and then 5. Or I could choose 3 and then 5 and then 2. So there's 3 possibilities for my first one, 2 for my second, and 1 for my third. Or in other words, there are 3 factorial ways to order those 3 books that I chose. And because they're all the same, I need to get rid of that. So there are 60 ways to permute the books. But I also know that there are 3 factorial ways where each selection of books is really a duplicate of one another if order doesn't matter. And 3 factorial is 6, right? There's 6 different ways to rearrange those. So 60 divided by 6 gives us 10 different ways to do this. In general, the formula for combinations is, if you want to choose r elements from an n-element set, and the order in which you choose them does not matter, then there are n factorial divided by n minus r factorial, and also divided by r factorial ways to do this. So notice that this really is the NPR, the number of permutations, divided by r factorial, as we just saw in our last example. Let's look at an example of playing cards. The game of euchre is played with a 24-card deck. The cards involved in the game are 9 through ace in each of the 4 suits. Each person in euchre is dealt a 5-card hand. My first question is, how many different 5-card hands are possible in this game? How do I know I should use combinations instead of permutations? When I'm dealt a hand in cards, it doesn't matter what order those cards go into the hand in. The person dealing could have dealt me a 10 of clubs on the first card, or the third card. It doesn't really matter. Once I get my 5-card hand, I can look at it and rearrange them however I want. So, since order doesn't matter, I will be using combinations in this particular problem. So, let's look at my set of cards that I can be dealt from. There are 24 cards in the deck. That's my list or set that I'm going to be choosing things from. Therefore, I will have 24 be n in the formula that we just looked at. And how many am I taking from that? Well, I'm being dealt a 5-card hand, so that means that my r is going to be 5. Therefore, 24 factorial divided by 24 minus 5 factorial times 5 factorial. 24 math probability NCR 5. So 24 choose 5. That is 42,504. So let's look at part B. How many different 5-card hands are possible where the hand is only made up of spades and hearts? I'd like you to try this problem on your own. Please pause the video and give it a shot. Okay, welcome back. So, well, let's think about what this means. It means spades and hearts. That's half the number of suits in a deck of cards, right? Because ordinarily there'd be diamonds and clubs also. So that means we've got half as many cards to deal with, to choose from, that is. So that's going to give us 12. So we'll have 12 choose 5, which you can plug into your calculator and get the answer. We will now look at a more complicated example of combination problem. In this example, we will look at how we decide whether or not to multiply or add combinations in more complicated problems. So here's the scenario. You're helping your brother plan the buffet table for his wedding. The caterer has a menu with 12 meat dishes and 5 vegetarian dishes available. Your brother wants 4 meat dishes and 2 vegetarian dishes at his wedding. So how many different possible buffets can you make? This is problem A. Well, let's think about this. He wants 4 meat dishes. There's 12 different choices for meat dishes. And it probably doesn't matter what order you choose them in. You'll still have those same 4 meat dishes at the wedding. I mean, unless you want to, like, number them on the table or something like that, in which case this would actually be a permutation problem. But let's assume that's not the case. Let's just say you want to choose 4 of them. Well, that's 12. Choose 4. How many vegetarian dishes are available? Well, there's 5 to choose from. Your brother wants 2, so that means there's 5. Choose 2 vegetarian dishes. Well, let's think about the fundamental principle of counting for a second. That says that if you have a certain number of ways that one event can happen, and a certain number of ways that another event can happen, then the way that both those events can happen is just to multiply those two numbers of ways together, right? So here, we have this number, of ways that you can choose meat dishes, and this number of ways that you can choose vegetarian dishes. So the number of ways that you could choose both meat and vegetarian dishes together is just this times this, right? 12 choose 4 times 5 choose 2, which, again, we'll pull up our calculator for. And so that's 12 choose 5, and then we'll multiply that guy by 5 choose 2, giving us 7,920. That's a situation where we're going to want to use multiplication to solve the problem. Let's look at this other example because it's going to contrast that. So, what if your brother had a lot of vegetarian friends? So, he just wants to ignore meat dishes altogether, and he says he wants at least 3 vegetarian dishes. How many ways can you have at least 3 vegetarian dishes on the buffet? What does it mean to have at least 3? Well, that means you could have 4, right? Or you could have 3, or you could have 5. But you couldn't have 2, because that's less than 3. And also you couldn't have 6, because, well, there's only 5 different possible vegetarian dishes available in the first place. So really the way to deal with this is, let's look at the number of ways that you could get 3 vegetarian dishes. Well, that's 5 choose 3. But then let's also look at the number of ways that you could choose 4 vegetarian dishes. That's 5 choose 4. And then let's look at, if you chose all 5, that's 5 choose 5. Well, 5 choose 3. We just did that with the book example. That's 10. And 5 choose 4. That's 5. And 5 choose 5 is, I'm going to let you think about this. I think you can figure this out. Pause the video. Welcome back. 5 choose 5 is 1. The reason? How do I choose 5 things from a set of 5 things? Well, there's only one way I can do it. I just take them all. What do we do with these numbers now that we have them? Well, we have the possibility of choosing 3 dishes, and if that's the case, there's 10 ways to do it. So we could make a list of those 10 ways, and then we want to add on to that list another 5 ways we could do this, and in the case that we had 4 dishes. And then finally, we want to add the possibility of having all 5. So really, this is a case where we add our possibilities. When you see words like at least or more than in problems like this, it usually means that you're going to be adding. Another really important distinction is and. So in this case, wanting 4 meat dishes and 2 vegetarian dishes sort of signifies that there's 2 events that are going to go on. And so and gives you multiplication like we have above. Whereas down here, they could have 3 vegetarian dishes or 4 vegetarian dishes or 5 vegetarian dishes, and so here or gives you the plus. With any word problem, you know there are exceptions to this, but I hope that's a good guideline for you. Let's look at an example where you can use subtraction to strategically make a problem easier. Your brother and his wife decide that there is no expense to be spared for their guests. They tell you that they want at least 3 meat dishes. Your brother and his wife want to have a lot of meat dishes, at least 3. They could choose up to 12. We could do what we did last time, and we could say, how many ways are there to choose 3 meat dishes? Alright, how many ways are there to choose 4 meat dishes? And do that for all of them, and add them all up. But that would take a long time, so let's not. Let's look at this in a different way. I'm going to go back to the idea of the tree diagram and the fundamental principle of counting. Let's look at meal number 1. Maybe it's chicken piccata. I don't know. But the point is that you could either take meal number 1 and put it in there, accept it, I'll put a little yes here, because you want it. Or maybe you don't want chicken piccata. No. Well, let's say you didn't choose chicken piccata. Well, then we look at meal number 2. And meal number 2, we could either say, yeah, I want meal number 2. Maybe it's beef stroganoff. Or no, I don't want meal number 2. And if you'd said yes to meal number 1, you'd have the same options, really. You could say, yes, I want beef stroganoff. Or, no, I really don't want beef stroganoff. And then, once you'd made that decision, you could go on to meal number 3. Maybe meal number 3 is smoked salmon. No, I don't want smoked salmon. Yes, I do want smoked salmon. And for each decision that you'd made prior to that, really, you'd contemplate meal number 3 anyway, right? For each meal, you have 2 different choices. You have either the choice of taking it or not taking it. So that's 2 options for the first meal, times 2 options for the second meal, times 2 options for the third meal, times 2 options for the fourth meal, and we'll do that for all 12 meals. That's the same thing as 2 times 2 times 2 times 2, 12 times, or 2 to the 12th power. So there are 2 to the 12th power ways to choose different meat dishes. However, those 2 to the 12th power ways include not choosing anything, right? I could just say no to all the dishes, and we don't want those situations. We need to have at least 3 meat dishes. But what we can do is say 2 to the 12th is the way that we can do any number of meat dishes. I need to get rid of the 3 possibilities where there's no meat dishes, where there's 1 meat dish, or where there's 2 meat dishes. Those are all a problem. Well, the number of ways that you can choose no meat dishes, there's only one way to do that, right? In fact, it's 12, choose 0, which is 1. How many different ways are there to choose one of the 12 meat dishes? Well, that's 12. Choose 1. That's 12. How many different ways are there to choose 2 meat dishes? That's 12. Choose 2. Which I don't actually know what that is, but my calculator does. $66. So my answer here really is 2 to the 12th minus 1 minus 12 minus 66, which is 4,017. Alright, so in this lesson we learned how to count using combinations in situations where order does not matter. Then we learned how to decide whether to use addition, multiplication, or sometimes subtraction to solve a combination problem. See you all in class.